can see me.
Yes.
Okay, so hello everyone. My name is Teodor, and I'm a PhD student here at Chalmers under the supervision of Jan and Helena. And I am around in about halfway of my research right now. So in this talk I'm going to talk about what I've done so far and my future plans, so to speak. So my main interest is in my new approach is going to be deep semi-supervised learning. But in I've been working with semi-supervised learning in general mostly, or labeling, or however you want to talk about it. So, so as you might know, supervised learning and unsupervised learning are the most common learning paradigms out there. So, and as you might know, supervised learning utilizes label data, and the more label data you have in your data set, the better results you usually get, especially for deep learning algorithms that usually needs a lot of data. But in industry, as you might know, you might often often find data sets with a lot of missing information and labels. And then we have unsupervised learning, which utilizes only unlabeled data to learn patterns. And most often unlabeled data is pretty easy to find, okay, right? So then we have the main question we have is, can we learn from both labeled and unlabeled data, and can this improve supervised classification? And the answer is yes. So there are two main approaches that I've been looking to. At first, active learning and then supervised learning. So active learning is when you train a supervised model and then you query unlabeled instances according to some measurement called a query strategy. And each query strategy measures the informativeness of each unlabeled instance, and then the ones with the best measure, they are usually included into the label data. So you label that data point and you put them in the label data set, and then you retrain the model, and you repeat this until you reach some kind of stopping criteria, or you have you get the best accuracy possible, or maybe you have some other criteria, like you should stop when you're out of time or out of workload or something. Yeah. And then we have, so it includes some manual effort as well. And then we have semi-supervised learning, which utilizes both labeled and unlabeled data. And so the main purpose of semi-supervised learning is mostly to improve upon supervised learning, not semi-supervised learning, sorry. Supervised learning. So can it improve supervised learning? So in my research, in the beginning, I was looking through different papers and investigated what algorithms are actually used in practice. So I found that uncertainty sampling and density-weighted methods is one category that I put them in. So you sample by how uncertain the data points are and their density, and then you have sampling by clustering, and then you also have something called query-based method, where you have different learner oracles that labels data, and then you query so you label them according to how they agree, basically how these different committees agree on the labeling. And we found many applications for this, like image sequence recognition, content-based information retrieval, word sensitive segregation, text classification, part of speech tagging, and so on. A lot of applications, and same for query-based methods, a lot of part of speech tagging, sentiment classification, document classification, power factor predictions, edge catching in mobile traffic, among others. So a lot of classification stuff. And then we have also a lot of different semi-supervised learning algorithms. So we have, for instance, co-training and multiview learning. So co-training involves also that you have several different classifiers, and then you label the data according to how these algorithms agree on a certain label. And then you have multiview learning, which is when you can view an instance in different views. So maybe you can look at the instance using these features, and then there's another way to look at it using different features and so on. So we found some algorithms that were popular here: semi-supervised discrete hash models, ensemble co-training, multiview individual and shareable features engineering, co-forest, multiview multiple view co-training, and among others, a lot of them. And then we have something called mixture models, and there's also supervised mixture models, but in semi-supervised ones you will have to include also labeled and unlabeled instances, and this will make it very difficult to optimize. So you most often you also use the EM algorithm for that. So we have some model here: EM algorithm for model transition, cross-language using IG filtering and naive base classifiers, and mixture models using unified objective functions, and semi-supervised kernel GG mixture models. And then we also have something called semi-supervised support vector machines. So they work like supervised vector machines, but they also incorporate some unlabeled data. You basically, to the objective function, you just add an term that includes unlabeled instances as well. So we have a lot of algorithms here, and which are graph-based, one-class support vector machines, graph-safe support vector machines, optimal margin with optimal margin distributions, collaborative support vector machines, Laplacian support vector machines, twin support vector machines, fast Laplacian twin vector machine, asymmetric Laplacian support vector machines. Yes, a lot of different ones. And then we have probably the one that I've studied the most. These are the graph-based models, and they are used to basically how they work is that they create a graph using all these instances. So you have a lot of instances, and you like color them according to what label they have, and then you have some unlabeled instances and they have no color at all, and then you measure the distance between the closest labeled node and according to some distance metric, and then depending on how close they are, you label them accordingly to which node it's closest to, and so on. And here we have a lot of algorithms because they are very they still developed these pretty recently, so they are kind of popular, and there's a lot of research in them, but they suffer from a lot of computational issues. So for example, here we have compact graph-based label propagation, multi-graph-based label propagation, KNN sparse graph-based semi-supervised learning, prior-based, a lot of fancy name. Poisson learning is pretty popular, shoestring, sentiment value propagation, and so on. So there's a lot of things that have been done here. And here again, we have also very different applications. For example, code training can be used for image, a lot of image applications, medical image identification, also activity recognition and classification of dynamic networks, web pages, natural language processing, and graph-based models is also very popular on images and text, of course. And same here with mixture models, also images, text, and some other cool stuff, microalgae classification, anomaly detection, cross-language text classification, phonetic classification, data-driven structural health modeling. And then we have the semi-supervised support vector machines, a lot of cool things like face recognition, object detection, activity recognition, malware detection, lung diagnostics, and stuff like that. So now to some papers that we have written. So for example, when I read all these papers with all these algorithms, we found about 87 different data sets that they were evaluated on, and they were basically 4 different data types: image-based, text-based, and then also some sound-based data set, not that many, but a few of them. So we have image-based data sets, as you might know, pixelized images that are represented by a 2-dimensional array, and text-based data sets, basically texts that you have to convert to numbers, and sound-based data sets is where the data comes from image files, and then numerical data sets where you just have some numerical features, basically. And in one of the papers, actually 2 of them, we took 24 data sets, the most common, the ones that are most easy to get hold of, and then we evaluated them using 13 graph-based semi-supervised algorithms. And we had 8 image-based, 8 numerical, and 8 text-based data sets. And then we divided them into 2 different variables, so manual effort and data type. So we compared them in terms of how many labels do we need in order to get the most accurate and the highest accuracy in our algorithms. And then we also looked at individual data type. Do they work better for text-based or image-based or numerical data sets? And then we use something called the Bayesian-Bradley-Terry model to rank them according to which one has the highest accuracy. And it turns out that the algorithms got the highest accuracy on image data sets, very high, like some of them had almost 100%. And the lowest ones text data sets didn't perform as well, still pretty high. And when it came to available labels, it was actually highest accuracy when you have 50% or 25%, which is quite interesting. But it's also, it should be, that's like how we want it to be. We want semi-supervised learning to perform better when we have few labels. I mean, that's the purpose of it. So that was good, pretty good results. And then we have another paper that we wrote also, evaluation of data sets. So here we took basically the same data that we had in this empirical evaluation, but instead of comparing the algorithms, we compared what data set is actually best suitable for evaluating graph-based semi-supervised learning algorithms. So for that we use item response theory, something called item response theory. So the easiest example where you use this is that suppose that you are a teacher that are constructing an exam for students, and you want to evaluate the performance of the students. So how do you construct this exam? What questions are the best ones to put in the exam in order to evaluate the students the best? So basically we did the same, but we did the same with the data sets. So what data sets are best for evaluating? So according to our results, the only data sets that actually were suitable are the Reuters data set, which is a text-based classification data set. So it's from the Reuters newspaper, and then you classify different types of articles. And then you have the assumed data set, it's also a text data set. And then we have something called the Musk data set. It's a numerical data set that describes different mushrooms, I think it was. No, molecules, I think it was. And so according to our results, these two were the only ones that actually were suitable. And what I mean with suitable is that the algorithms performed very similar on the other data sets. So these data sets were the only ones where the algorithms actually performed very differently. So we did examine some benchmark data sets like MINST and Cypher10, which is very common to try out, but it turns out that they are not very good for actually evaluating algorithms. So we shouldn't actually use them. So that was pretty cool. So some conclusions and future directions of my research. So from what we can see, supervised learning algorithms have been developed alongside their supervised counterparts, but they also incorporate, with the difference that they also incorporate unlabeled data sets. And this is easier said than done in some of them. And the graph-based methods are the ones that have been mostly developed. They are intuitive but suffer from computational issues. But we have not included any deep learning models in our research so far. And semi-supervised machine learning models have the ability to outperform supervised learning algorithms, but only in certain scenarios. So sadly, it might be that they actually worsen the performance of the models also. And this is probably why we haven't seen them that much in research. In research we see them all the time, but not in academia or in industry. Sorry, except with the exception of semi-supervised neural networks, actually. So recently many semi-supervised learning algorithms have been developed for deep semi-supervised learning. Only like the past 2 years, a lot of them have shown up, which is actually after I started. So. Neural networks with unsupervised preprocessing, semi-supervised regularization, and deep generative models. And in these cases, the supervised baselines used for empirically evaluating the performance of these methods are really weak. So there's a very skewed perspective of the benefits of incorporated unlabeled data. So we need to do more empirical evaluations of these. And the thing also with these are that most of the semi-supervised learning algorithms, they assume very strong assumptions, but semi-supervised neural networks incorporate relatively weak smoothness assumptions. And so these have proven to empirically outperform the supervised counterparts. And it's also much easier to incorporate deep learning models and make changes in the cost into the loss terms into the cost function that you optimize during the learning procedure. And it's also there's a big also one reason why it's not widely used in industry is also that there's a severe lack of software packages for semi-supervised learning, so you'll have to do all the coding yourself most likely. And also there's one research topic, a second research topic is to mitigate the robustness of semi-supervised learning is to also apply automated machine learning on it. And AutoML has been successfully applied to supervised learning, but there has not been any applications to semi-supervised learning whatsoever, probably because there's no software for it. So yes, so that's it for me, I think. So in the future, I'm going to look more into, try to look into more deep semi-supervised learning, and I have found some very interesting algorithms that I intend to, that require very few labels, and they will have a very good accuracy. So, but that's for the future. Thank you.